Alright, so we're ready for today. Okay, so let's go over the quiz that you guys took last night, and you guys said it was hard. So let's go through the quiz, and hopefully you change your mind after I go over the solution, or maybe not, who knows. So for one of the questions, so in total there were 4 questions. You had 30 minutes, so I thought that timing was enough because none of them you had to solve it completely, but you still have to go through some computation, so I understand that was a bit of time consuming. So I'm not dropping a quiz grade because we only have 4 quizzes, so even if you didn't do so well, it's not so bad. One quiz wouldn't make a big difference, okay? So don't worry about it. So let's go over the quiz. So again, I encourage you guys to try to speak through your audio. That way I can answer your question much faster than me going back to the chat. Alright, so for the first or one of the question, we want to see which of the following statements are true. So you kind of have to solve this, right? So to come up with the solution, at least partially, you want to see what is the homogeneous equation, the corresponding homogeneous equation would look like. So you have 2, so wrong color. Okay, so 2 okay, so we have 2y to the 6th derivative minus y to the 5th plus 6y to the 4th derivative minus 3y to the 3rd equals to 0. So that looks like that option, right? That's true. And then for the rest, you kind of have to go and solve it, right? So what will be the corresponding characteristic polynomial? What do you guys have? Okay, you guys are quiet today. Let's start talking.
It would be 2r to the 6th minus r to the 5th plus 6r to the 4th minus 3r cubed.
Okay, and then how would you find the roots to this polynomial? So which method was useful for this question? Yeah, right, let's factor. So if I factor out r cubed, I will have 2r cubed minus r squared plus 6r minus 3 equals to 0. And then we have 3 roots, right? So r cubed will give us 3 roots, so but they're repeated. So we have r equals 0, that's repeated. And then the inside, you can factor it further by grouping. So we have r squared times 2r minus 1. And then the last two, if you group them, we pull out a plus 3. Then we have 2r minus 1. And then factoring it further, we have r squared plus 3 times 2r minus 1 equals to 0, and then r cubed equals to 0. So that's the furthest you have to solve this equation, and the rest is just picking which choice would fit into it. So if you look at the first choice, the function y equals ax to the 5th plus bx to the 4th plus cx cubed is part of the particular solution. Well, let's check, right? So the homogeneous solution, we have r. So if I were to write out the homogeneous solution of this, I would get, so yh, it's going to be, So we have r equals 0, that's repeated 3 times. So that's c1 plus c2 x plus c3 x cubed. So that's with the repeated root for 0. Plus, now the second one, r squared plus 3, that gives you complex roots, right? So you have plus and minus square root of 3i. So that would give us cosine of square root of 3x plus sine, well, I forgot the constants, so c4 and then c5, right? Sine of square root of 3x, and the last one is a real root, so we have another, so that'll be an exponential, plus c6 e to the 1/2 x. So that's how the homogeneous solution look like. So based on that observation, is this function, the first choice, is a solution?
Professor, shouldn't it be c3x squared? Because if we technically see like r cubed, that's like 0 to the 0, right?
Yep.
So the 0, 0 is like c1, c2x, and then c3 is just x squared is being repeated again.
Right, I made a typo. Thank you. So
No problem.
now we can answer the question because I had a typo, it didn't make sense. Is 1 a choice, a true statement? So how do we know if 1 is true or not? Alright, come on guys, you had the quiz last night. You have seen this question, you worked it through, right? You guessed the answers. So Aisha says 1 is true. Yes, 1 is true. Right? 1 is true because this is our YP. You can say one of the particular solution, which is a second degree polynomial. And then to make it different from the homogeneous, you would multiply it by x cubed. And that will make it different from the homogeneous solutions. Now, what about 2? So the roots of the characteristic polynomials are all real. That's not true because we just saw they're real and complex. So that's not true. And then the function y equals c1 plus c2x plus e to the 1/2 t is part of the homogeneous solution. Yeah, we have all of them, right? We have this one, and this one. So that's also true. And then 5, the function y equals ax cosine 3x plus bx sine 3x. Is that part of particular solution? Almost, right? It would have been if we didn't multiply by these x's. So that's not true. And then number 6, the function y equals a e to the x is not part of the particular solution. It is. You need that function because of this piece right here. So this is also a false statement. So the correct choice for this one would be 1, 3, and 4. So any questions on that?
Can you explain again why 1 is true?
So 1 is true because our YP1, which is for the 3x squared, that's a second degree polynomial. So you need ax squared plus bx plus c, one of the particular solution, right? Now, because these terms are exactly same as the homogeneous ones right here, so to make it independent from the homogeneous solution, we modify this by multiplying by x to the 3rd power. So then if you distribute this out, you will get ax to the 5th plus bx to the 4th plus cx to the cube. And all of those will be different from the homogeneous solution. Okay. Any other questions? Alright, so if there are no questions, moving on to the next problem. So here you have to set up a spring problem. So Again, you don't have to solve it. You just come up with the coefficients and just solve accordingly. So we wanted mu double prime plus gamma of u prime plus k times u is equal to some function g of t, and initial position of the spring and initial velocity applied to the spring. And you fill this in. So what's the correct answer for this question? What did you guys get? 1. Yeah. So you'll see after you plug in these unknown constants, you'll have 1 as the right choice. Okay, so if you want to see the detailed solution, I will be in my office hours tomorrow. Come by, I'll work them out for you. For now, I'm just going to write down the answers. And number 3. So, how do you do number 3?
Test for power series.
Right, the ratio test.
Yeah,
Yeah, it's fine. So you want to do the limit as n approaches infinity of a sub n plus 1 over a sub n, and you want to restrict this. Well, you'll get some value L, right? And we want that to be less than 1 in absolute value. So that way we have convergent. And once you do that, what do you guys get after you're taking the limit? Yeah, right. So it converges everywhere on the real line. And the last one, the recurrence formula. So here I didn't really have you solve a second order differential equations, but I just said play around with the recurrence. So I didn't think it was so difficult. But let's see. So what you want to do is you want to solve for the highest subscript. But before that, we need to shift these powers so that they all have same power. So I'm going to use a substitution, let's just say k, and then just rewrite it as n. K is going to be n minus 2, and for this one, k is going to be n. So then the first summation, we're going to have, if n is equal to 2, k is going to start at 0. If n is equal to infinity, k will also be infinity. And then we have n, that's going to be k plus 2, and then n minus 1 would be k plus 1, a sub k plus 2, x to the k minus the sum starting from k equals 0 to infinity, 2 times a sub k, x to the k equals to 0. And now we just group them together and try to solve for a sub k plus 2. So we have the sum starting from k equals 0 to infinity, k plus 2, k plus 1, a sub k plus 2 minus 2 a sub k x to the k equals to 0. Now we can solve for the subscript we want, which is a sub k plus 2. So that would give us, so we add 2 a sub k on both sides, and then divide by k plus 2 times k plus 1. So that's the recurrence formula. And if you were to choose an answer for this,
it's option 2.
yeah. Okay. So that was the quiz. Does it seem better now? So you at least see the answers partially. So I didn't really solve 2 and 3, but hopefully you can see how it's done. Alright, so Liana agrees. That's good. Alright, so that was your quiz. That was the last quiz. We have no more quizzes. Now we have an exam. Monday. No, sorry, not Monday. Tuesday. We meet Tuesday. We don't meet Mondays. Tuesday. Okay, so let's continue with our lesson from yesterday. We we started doing 5.4 where we talked about how to solve Euler equation. Euler equation, it's kind of like a second degree polynomial, okay? And then we were able to identify beta and gamma, and we make sure that the coefficient in front of x squared is 1, and then we can identify beta and gamma. So knowing all of that, let's do an example just to review what we did last time. So we're still continuing with 5.4, which is Euler equations and regular singular point. So this is still 5.4. So here's a problem for us to work on. So this is just briefly review what we did last time. So I want to solve the following initial value problem. So you can easily identify this is an Euler equation, right? Because you have a term involving x squared with the second derivative, x with the first derivative, and then the constant with the y term, okay? So just by looking at it, we can identify the initial equation. So we have r times r minus 1 plus beta r plus gamma equals to 0. So let's identify what is beta and what is gamma. What are those constants? Okay, so let's plug them in. So we have r times r minus 1 minus 10, no, sorry, minus 1 r plus 10 equals to 0. And then we try to solve this polynomial. We get r squared minus 2r plus 10 equals to 0. And you try to factor and see if it works. So this one doesn't look like it's going to factor. So let's use the quadratic formula. So r is going to be negative 2, so that's 2 plus and minus square root of negative 2 squared, that's 4 minus 4 times 1 times 10, everything over 2 times a, that's 1. So just by using simply the quadratic formula. And then what is this will give us? So we have 2 over 2, that's 1, plus and minus square root of, so we have 40, negative 40. So 4 minus 40, that's negative 36 over 2. And then if I simplify this, you see we have complex roots. 1 plus and minus square root of 36 is 6. Negative will give us I. So 6 over 2, that's 3i. So from here we identify A, and that's B. So the solution of this is going to be y equals x to the A, right? So that's x to the 1 times c1 cosine of b, b is 3 ln of x, plus c2 sine of 3 ln of x. So that's how the solution would look like. But because this is an initial value problem, we have to go ahead and compute what is c1 and what is c2. Any questions up to here? Is it making sense so far? Okay, thank you. So let's plug in those initial conditions. So we have y of 1 equals to 4. So that means x is 1, y is 4, so we have 4 is equal to x is 1, so 1 times c1. So if I plug in 1 for x, ln of 1 is 0. So all the inputs for sine and cosine are 0. So we have cosine of 0, that's 1, sine of 0, that's 0. So c1 is 4. Ooh, that's nice. Well, for the second condition, we need to compute the derivative of y. So let's do that. So y prime is going to be what? Product rule, right? So differentiate the first, which is x, keep the second, so we have c1 cosine of 3 ln of x plus c2 sine of 3 ln of x. Plus, now you keep the first and differentiate the rest. So we're going to have c1, oh geez, chain rule, right? So someone help me out. Let's get more space. So c1 is a constant. So cosine, derivative of cosine is negative sign. So we have negative c1 sine of 3 ln of x times the derivative of the inside. So that would be 3. Derivative of ln of x is 1 over x. So that's the first part. The second part, we're going to have plus c2, derivative of sine is cosine of 3 ln of x times 3 over x. Okay, not so bad, right? We managed to do it. And now we apply the initial condition, which is y prime of 1 is 0. So y prime of 1 is 0. So plug in, let me just double check I copied it right. Yeah. Okay, so plug in x equals 1, y is 0. So we have 0 is equal to, so when x is equal to 1, what happens to this derivative function? So this will go to 0, right? Because ln of 1 is 0, sine of 0 is 0. And then this will also go to 0 because of sine. The last one will survive. So what we really have is c1 plus 3c2. Yep. So that's what we get. Okay, and now we can successfully plug in what c1 was, which was 4. So we have negative 4 is equal to 3c2, which means c2 is equal to negative 4 over 3. Ooh, that's nice and neat. Okay, so we have our solution. Our solution to this, it's going to be y equals x times c1, that's 4, cosine of 3 ln of x, minus c2, that's 4/3, sine of 3 ln of x. So that's our solution to this. Any questions? Okay, so there you have an initial value problem with Euler equation. So that's what we talked about last time. So today we're gonna extend this and talk about regular singular point, and then we're gonna slowly move on to 5.4, where we're gonna seek series solution near regular singular point. So before that, we want to know what are regular singular points. Well, just in general, what are singular points, okay? And then we'll identify them as regular or irregular. So that's the next thing we want to do. So singular points. So suppose you have the following differential equation. So for the differential equation, p of x y double prime plus q of x times y prime plus r of x times y equals to 0. Okay. X naught equals 0. Okay. Well, let's not say 0 yet. So let's just say x naught. X naught, so it could be any value. It doesn't have to be necessarily 0. X naught is a regular is a singular point, not regular, just a singular point, if the function p evaluated at x0 is equal to 0. So that's what the definition of a singular point is, okay? Before we talked about ordinary point, which means if you plug in x0 into p of x, it's not equal to 0. That's what an ordinary point is. And singular point is just when p of x evaluated at that given point is equal to 0. So that's the only difference between these two definitions. Now let's classify it. We're going to classify it as a regular singular point. So what's a regular singular point? So we're going to classify this by limit definition. So we're going to take the limit of the following functions, okay? So we take two limits. One, you take the limit as x approaches x0, that singularity, of x minus x0 times q of x over p of x. If this limit, and we take another limit as x approaches x0 times x minus x0 to the second power, and r of x over p of x. So now we take this limit. If these limits are finite, both of these, so if 1 and 2 are finite, meaning not infinity or not undefined, then we say that x0 is a regular singular point, RSP. Okay? If it's not finite, then it's irregular. Okay? So otherwise, x0 is irregular. Irregular singular point. Okay. So the key idea here is that these limits are finite. Okay. So now I will show you an illustration where are these functions really coming from. Okay. So we're gonna tie this with Euler equation and introduce another name, and then I'll reintroduce this with Euler equation that we worked with earlier. So suppose we take this equation right here. Let's call this equation 1. Okay, so the differential equation p of x y double prime q of x y prime plus r of x times y equals 0. So take that differential equation and divide through p of x. Okay, so if you do that, so we have this. So take equation 1. I just want to show you a quick illustration of why these limits are finite and why does it work, okay? And then we'll get started with examples. So if I divide by p of x, I have y double prime plus r of x, no, hold on, q of x, that's first. So we have q of x over p of x times y prime plus r of x over p of x y equals to 0, right? So that's the equation we get if we divide equation 1 by p of x on both sides. Now what do you want to do? You want to make this like an Euler equation, right? Where you have x squared term with second derivative, x term with the first derivative, and then the constant term and the rest. So what are we going to do? We take this and we multiply this by x squared. So we multiply with x squared. So then what happens? So what happened is that we get the following. We have x squared y double prime plus x squared q of x over p of x times y prime plus x squared times r of x over p of x times y equals to 0. So that's the expression we get when we multiply both sides by x squared. Now I'm going to group the second and the third term in this way so that I can show you something very nice. Okay, so check this out. So the first one, we just keep it as it is. For the second one, I'm going to pull out an x from x squared. So we have x times, and then we have this term, x times q of x over p of x. Okay, so I just rewrite times y prime plus, now for the last one, I'm just going to group it in a bracket. So you have x squared times r of x over p of x times y equals to 0. Well, now, what do you notice? What do you notice with this kind of modified Euler equation with the limit definition we have? So maybe not so clear yet, but suppose x naught, the singularity you're looking at, is 0. Okay, so just suppose that. Now, if x naught is 0, on the limit definition, x minus x naught will drop, right? So you have x times q of x over p of x. And the second limit definition, again, x naught will drop because of 0. You will have x squared times r of x over p of x. Aren't those the same coefficient we have in the Euler equation? Do you guys see that?
Sorry, can you repeat that one more time?
So if I plug in x naught equals 0 into 1 and 2, right? So these guys are 0. So if they're 0, what you really have is x times q of x over p of x. Isn't that what we see here? Right? And the second one, you see you have x squared times r of x over p of x. So that's right here. Now, in Euler equation from the past, we said it is Euler equation if it can be written in this form, x squared plus x squared double prime plus beta x times y prime plus gamma of y equals to 0. So what you see here is this is really our coefficient beta, and this is our coefficient gamma, right? So it looks exactly like an Euler equation. So that's why, and we want these limits to be finite. So that's why this condition has to hold. In order for the singularity to be regular, you want these two limits to be finite because they really correspond to the Euler coefficients. So in this subtopic, we call beta and gamma Euler coefficients. So beta, which is defined as the limit as x approaches 0, so we're plugging in x naught to be 0, and then we have x times q of x over p of x, and you want this to be finite, and then we have gamma, which is again a limit definition as x approaches 0, x squared times r of x over p of x. So very important for 5.5. So we'll just keep this in back of our head as we proceed to 5.5. Hopefully you will recall and remember Euler coefficients are beta and gamma, which can be defined as these following limits. And these limits, if they're finite, then we know that particular singularity is a regular singular point. Okay, so that's the takeaway from these two concepts. So let me know if you guys have questions. So let's do an example. Okay, so stop me if you have a question. So let's show that. Let's find some singularities. So here's our first example on this. So determine the singularities of the differential equation. So given 2x and then x minus 2 square y double prime plus 3x y prime plus x minus 2 y equals to 0. So once you have determined the singularity, then classify them. Meaning, is it regular or irregular? Okay? So how do we determine singularity? What was the definition? Let's pull up, right? We said that a point x naught is a singular point if p of x naught is 0, meaning the function in front of your second derivative, whenever it is 0, that's the singularity. And then we classify them by taking the limits. So, 1. What are the singularities? So when is p of x equal to 0? Right? So p of x is this function right here. That's p of x. We want to know when is p of x equal to 0. So p of x is 0 when 2x times x minus 2 squared is equal to 0. So we know when x equals 0, that's when it is 0. And we also know it is 0 when x is equal to 2. So we have total of 2 singularities. So we were able to determine them. Now we're going to classify each one of them. So let's classify 0. So number 2, let's classify them. So let's classify x not equal to 0. What kind of singularity this is? So we take the limit as x approaches x naught of x minus x naught times q of x over p of x. And then we're going to take another limit as x approaches. So we take 2 limits per singularity. And this will be x minus x naught square r of x over p of x. And let's plug in what are these components. X naught is 0. So we have the limit as x approaches 0, x minus 0, so that's just x, times q of x. So in our function, q of x is the second function. So this is q. And this function right here, this is r of x. And now let's plug them into the limit definition. So q of x, that's 3x over p of x, that's 2x times x minus 2 squared. And then back to calculus. Take the limit. Where is this limit? How did you get 1? Mm-hmm. So you change your mind. Got it. So you see the limit is not 1. It's going to be something else. But it's finite, right? So what's the limit? 0. Mm-hmm. Exactly, because these x's will cancel out. So you'll be left with 3x over 2 times x minus 2 squared. And then when you substitute 0 for x, you get 3 times 0 over negative 2 squared, and that's okay. That's 0 over a number, so it's 0. So it's finite. Okay, success. Let's take the second limit. So we plug in x naught is 0. So we have the limit as x approaches 0 of x squared, because x naught is 0, times r of x. Our case, r of x is x minus 2 from above. And on the bottom, we get p of x. That's 2x times x minus 2 squared. Now, take the limit. What is this limit? So this is also 0. Can you see that? Yeah. Yeah, and then the other one will go to 0. So this is also finite. So success. So what do we conclude? We conclude that x naught equals 0 is a regular singular point. So that's the first conclusion we draw. And you do the same thing for x naught equal to 2 and see what happens. So let's do that. So let's classify the second one. So x naught equal to 2, we want to take the limit as x approaches x naught, which is 2, x minus 2 times q of x, that's 3x over 2x times x minus 2 squared. What is this limit? So if I were to simplify, right, x minus 2, one of the factor will cancel. So you have the limit as x goes to 2 of, and then the x's will cancel. So that's 3 over x minus 2. So as we plug in x equals 2 for this limit, what happens? Alright, it's undefined. So this limit doesn't exist. So what does that mean? We don't need to compute the second limit, because if one does not exist, it doesn't matter if the other one is finite. You're still not going to be regular. So we will say, therefore, x not equal to is not regular. So it's going to be irregular. Say irregular. How many r's are there? 2. Irregular singular point. Does this make sense, guys? Okay. All right. Let's do another example. Let's check this one out. So let's try. So again, same direction. So let me see if I can copy this. So we want to determine what are the singular points and then classify them. Oh, perfect. Okay, so this is example 2. So let's consider this differential equation. Let's do x squared times 1 minus x squared y double prime plus 2x y prime plus 4y equals to 0. So you want to determine them and then classify them. Okay. Alright, so to determine what are the singular points, okay, let me give you a few seconds. Just process through, okay? Okay, so let's let's do this. So, what are the singularities? 0 and 1. Okay, thank you guys. So we have two of them. 0 is coming from x squared and 1 is coming from 1 minus x, because that's when p of x is 0. Okay, so now let's classify them. So for x not equal to 0, we take the limit. So we take the limit as x approaches x naught, which is 0 in this case, x minus x naught. So okay, so what do we have? We have x times q of x, that's 2x, over p of x, that's x squared, times 1 minus x squared. And let's take the limit. So we simplify first before taking the limit. Limit as x goes to 0, 2x and x will cancel out, so you have 2 over 1 minus x squared. And what is this limit? So if you plug in 0, this limit will just be 2. Okay. So this is finite. Nice. Let's take the next one. So we take the limit as x approaches 0 for x squared times 2, no, r of x is 4 over x squared times 1 minus x squared. And what is this limit? So as I simplify, I have 4 over 1 minus x squared, and that will give us 4. So again, finite. So because they're both finite, we conclude that x naught equals 0 is a regular singular point. Okay. Any questions? Let's do the second one. So x not equal to 1. So we take the limit as x approaches 1 of x minus x naught, so x minus 1 times 2x over x squared times 1 minus x squared equals. Now, in order for us to take this limit, we have to simplify. But because x minus 1 and 1 minus x is differed by a negative sign, we have extra negative left. So we have the limit as x approaches 1 of negative 2 over x times 1 minus x. And what is this limit? Undefined, so, right, or DNE. So we would say, again, this would be irregular. So x not equal 1 is irregular. And so on, right? So you got the basic idea, how to classify them and how to determine them as well. So something useful for 5.5. So any questions on this? Okay, so if there are no questions, we're moving on to the next section, which is 5.5. So 5.5 is the last section for chapter 5, and then we move on to chapter 6 and then chapter 10. So we're pretty much done with the course. So pretty excited, right? Are you guys excited? Okay. Alright, so someone is excited. I'm excited too, so we're all excited. Okay, so 5.5. On 5.5, we're going to study series solutions near regular singular point. So regular singular point. And this is in the textbook, it's called part 1. There's also part 2, which is 5.6, but we don't cover that in this course. So for us, it's just, this will be the end of it, okay? So, well, just like I said earlier, once we know we have a regular singular point, well, we know by two ways, right? We can write out the Euler coefficient, which is really these limits that we computed. So I show you guys, we can show that x naught is a regular singular point by computing these corresponding limits. And once these limits are finite, then they're actually the corresponding Euler coefficients for Euler equation. And once you have the Euler equation, you can write out the initial equation. And from there, we can get the roots R1 and R2 for our specific solution. So that's the idea we want to carry over to 5.5. What are we after? Well, we want to solve a second order linear differential equations in the neighborhood of a regular singular point. Only regular, so the limits are going to be finite. So we want series solutions near regular singular point x equals x naught, and we're going to assume that x naught is going to be 0 for convenience, because if it's not 0, then you'll be shifting the power series and the computation can get really messy because we're doing it by hand. So we're going to consider x naught is 0 for convenience. So that's the key idea. And this would be a regular singular point. So suppose you're given the differential equation. The usual, so you have p of x times y double prime plus q of x times y prime plus r of x times y equals to 0. So suppose you're given that and x naught equals 0 is a regular singular point. Now, how would the solution to this differential equation would look like? Well, we're going to assume the following, okay? So by reduction of order, we're going to assume the solution looks like y equals x to the r, right? Because these are going to be, we can always find the corresponding Euler equation, and the solution to the Euler equation is x to the r. And we're going to assume, so it has that form, x to the r, times a nice function, v of x. That's what the solution to this differential equation would look like. We're assuming this, where v of x is a very nice function, meaning it's a power series, it's analytic, and you can differentiate this as many times you want. So v of x is an analytic function. Okay, so the word analytic, it means it's a power series. Or think of it's a nice function. Okay, so nice. Nice meaning you can differentiate this as many times you want. You want to go for the 10th derivative, do that. So the idea is we're multiplying by a nice function. So, well, we know how to represent power series, right? So that means v of x is the infinite sum starting at n equals 0 to infinity, an, x minus x naught, but x naught is 0, so it's just x to the n, okay? And that's what I'm going to substitute into the solution we're assuming. So that means our solution is going to look like x to the r times this infinite sum. n equals 0 to infinity a n x to the n. Well, you can leave it like this, but for again simplicity, we're going to push x to the r inside the summation and combine it with x to the n. So we have the sum from n equals 0 to infinity a n x to the n plus r. So that's how the solution form would be if we're working with series solution near regular singular point. Okay. Well, now that we know what kind of solution we're working with, or at least what we're assuming, we can go ahead and take its first and second derivative and plug it in, right? That's the usual drill. So how would the expression of the first derivative would look like for this? So remember, r and n are real numbers, so they're just numbers. So if that's the solution form, then its first derivative, it's going to be the sum starting at n equals 0 to infinity. I'm going to bring down n plus r times a n x to the n plus r minus 1. That's the first derivative. And the expression for the second derivative is going to be the sum starting at n equals 0 to infinity n plus r times n plus r minus 1 a n x to the n plus r minus 2. So these are the expressions we're going to plug in for the first derivative and second derivative. So I know what you're thinking. These expressions are long, but trust me, you can manage. We all did it. You can do it too. So don't panic. I'm gonna go through an example where we keep track of the indexing. So I will show you the long way first, and then we'll just drop the indexing because you'll see there's no point in this course, at least. We're okay to ignore the indexing when we're seeking the power series solution, okay? But I will show you both ways for two examples. Now another thing to keep in mind. When you're looking for series solution near regular singular point, you will be asked to show that x naught is a regular singular point. And how do we show that? Well, we show that by computing limits, right? So in this section, every question will ask you to show that x naught is a regular singular point. So you would show x naught equals 0 is a regular singular point by computing limits. And then once you have shown that, we're going to connect this with Euler equation, okay? So once you compute the limit, you get those two corresponding coefficients. So I'm going to rewrite them. We had beta, which corresponded to the coefficient of y prime, right, times x. So this was the limit as x approaches 0 of x times q of x over p of x. And this is finite because we want beta to be finite, so we have an Euler equation. And then we said we can also get another Euler coefficient gamma by doing the following limit as x approaches 0, x squared times r of x over p of x. So these are the Euler equations. Once we have these coefficients, we then have a corresponding Euler equation, which would then look like x squared y double prime plus beta, which you just computed by limits, x y prime plus gamma times y equals to 0. And then from here, you can write out the initial equation, which is the polynomial, the characteristic polynomial of this. We call it initial, and I'll show you where this terminology is coming from very soon. So we have r times r minus 1 plus beta r plus gamma is equal to 0. So we have that. And then from here you can find r1 and r2 if they're distinct. Most likely they will be distinct. Probably. Okay, so we can do all of this. Okay. Now let me give you an example so that way I don't just throw in information without examples. So let's do an example and let's compute the corresponding Euler equation first, and then we'll seek the power series solution. So I did copy a question somewhere. So it's not here. It's not here. It's here. Oh, nice. Okay. Actually, no, let's hold on to this problem. That problem is pretty long, so I'm going to hold on to that question. Let's start with something simple and then we can get to that problem. So we'll probably do that next time. So let's start with this example. So here's our first example. So given the differential equation 2x squared y double prime minus xy prime plus 1 plus x times y equals to 0. So suppose you're given this differential equation. Okay, so here are the following we want to do. Show that x naught equals 0 is a regular singular point. Okay, so we can do this by taking limits, and once we have the limits, those values that we get for limits will be the beta and gamma for our corresponding Euler equation. So the second step is to write out the corresponding Euler equation. Okay, and then 3 is going to be compute the recursion formula, so recursive formula for the series solution corresponding to the larger root. So I'll explain what this means as we go along. And then the fourth step is to compute first 3 non-zero terms of the series solution with a0 equals 1. Okay, so I think this would simplify a little bit by putting a0 equal 1. Alright, so we'll take a few seconds break and then we'll start. Okay, so we want to show that x naught is a regular singular point. Well, we go ahead and take the limit. So part 1. So 1, okay, so we take the limit as x approaches 0 of x times, so in this case, our q of x is negative x, so that's negative x, over p of x, that's 2x squared. So what do we get as we take the limit of this? So you would see that x and x on top would cancel with the x squared on the bottom, so you'll have negative 1/2. So the limit of a constant is just a constant. So we computed the first limit, and we said that the first limit always corresponds to beta. Now let's take the second limit. Limit as x goes to 0 of x squared times r of x, that's 1 plus x, over 2x squared. And then by simplifying this, we have the limit as x goes to 0. X squared will cancel out. So we have 1 plus x over 2. As x equals to 0, we have 1/2. And that corresponds to gamma. So because these limits are finite, we conclude x naught is regular singular point. So any questions on the first part? Okay. Now for the second part, we want to write out the corresponding Euler equation. Well, we know the Euler equation is x squared y double prime plus beta xy prime plus gamma of y equals to 0. Well, we already know what these beta and gamma are equal to for this particular example. So we just have to plug them in, right? So here is beta and here is gamma. Let's plug them in. So for the second part, our corresponding Euler equation is going to be x squared y double prime minus 1/2 x y prime plus 1/2 y equals to 0. And there you go. That's the answer to part 2. Any questions on this? Now, I should have added an extra part to this. So write out the corresponding Euler equation and one more. And let's find the roots, okay? So find the roots. Because that's quick. We can do that, right? We learned that in 5.4. How do we find roots to this Euler equation? Right, so we get r times r minus 1, right? Minus 1/2 r plus 1/2 equals to 0. That's the initial equation, or the polynomial corresponding to the Euler equation, right? We did that last time, so I hope you guys still remember that. Does this make sense so far? Are you guys with me? Okay. Well, let's find the roots, right? So to find the roots, we're going to multiply both sides by 2 so we can get rid of these fractions. So by doing that, we have 2r times r minus 1 minus r plus 1 equals to 0. And then continuing to factor this, we have 2r squared minus 2r minus r minus 3r plus 1 equals to 0. Okay, so factor this. Can we factor it? I think we can, right? 2r and then r minus 1 plus 1. I think that will do. Let's just double check. 2r squared minus 2r minus... Hold on. Why doesn't it work? Oh. Oops. Yeah, that will work. Yep. Perfect. Thank you. Alright, so we found our roots to this polynomial. We have 2 roots. R is equal to 1 and 1/2. Perfect. We're going to hold on to this until we have a recurrence relation. So this will be hold on until the recurrence relation. Alright, so now moving on to the next part, which is now compute the recurrence formula for the power series solutions corresponding to the larger root. So let's set up the power series solution, and then I will show you how to get to the recurrence formula. So that's the next thing. So what are we going to assume? How does the solution look like for a regular singular point? But we said if we were doing regular singular point, our solution will have the form y equals the infinite sum n equals 0 to infinity an x to the n plus r. That's how the solution would look like near regular singular point. Now compute its first derivative, so we have y prime is equal to the sum n equals 0 to infinity n plus r times an x to the n plus r minus 1. And then the second derivative, it's going to be the expression n equals 0 to infinity n plus r times n plus r minus 1 an x to the n plus r minus 2. So these are the substitution we're going to make for the first derivative, second derivative, and y. Any questions up to here? Okay, so we're ready to plug this in. So be very patient with yourself when you plug these expressions into the differential equation. So I'm just going to go ahead and copy this because it's hard to just keep going back and forth. So let me do that for the next few seconds while you meditate on this. Okay, so there we have it. We have our differential equation. Now plug in these expressions for summation. Now for this problem, I am going to keep track of the indexing, but later on we will stop doing that. So for this one, be very patient. So we have 2x squared y double prime. So I'm going to go ahead and distribute the y for the last term, so that way we have two different expressions instead of one. So just rewriting one more time, we have 2x squared y double prime minus xy prime plus y plus xy equals to 0. Okay, now let's plug in these summations. So we have 2x squared times the sum starting at n equals 0 to infinity n plus r times n minus n plus r minus 1 x an x to the n minus n plus r minus 2. So that's the first part. And then for the second one, we're going to do minus x times the summation. So here we're plugging the first derivative, so we have n equals 0 to infinity n plus r times an x to the n plus r minus 1. That's the second term. Now the third term is just y, so that's just the sum from n equals 0 to infinity an x to the n plus r. And then the last term is x times y, so that would be plus x times the sum n equals 0 to infinity an x to the n plus r. Everything is equal to 0. Alright, that was good. Hopefully there's no mistake. You don't want to make mistake with these questions. Alright. So now the next thing you want to do is, if there is an x in front of the summation, you push them inside so you can combine it with the power of x. Okay, so just like we did before with the regular singular point, you do it again for this one. The only extra term we have is x to the r, so that really modifies our answer a little. So I'm going to go ahead and combine all the x's. So I'm going to combine this one with, I'm going to push this inside, combine it with that. And then I'm going to push this one inside, combine it with this. And the last one, I will push this inside and combine with that. So those are the next steps I'm going to take. So check this out. So we have 2 times the sum n equals 0 to infinity n plus r times n plus r minus 1 an x to the, well, now the power of x is going to get modified. We have a positive 2 and a minus 2. They cancel out, so it's just n plus r. Okay? And then for the second one, we have minus the sum starting at n equals 0 to infinity, n plus r times an x to the, now as you push the x inside, the negative 1 power will cancel, so this is also just n plus r. And the last one is simply just same thing, so rewrite an x to the n plus r. And the last one, as we push the x inside, we have the sum from n equals 0 to infinity an x to the n plus r plus 1 equals to 0. So we get 1 extra power on x. So that's how it looks like after you push all the variable inside the summation. Let me know if you guys have questions so far. So I want you to follow through the entire problem. That way we can work with this. Okay, so in ordinary series, we start shifting, right? What we did was we arranged the power to be k, x to the k. In this one, we want the power to be k plus r. That's the power we want. So I want to have the power k plus r. So we're going to rewrite. So we're going to let, if we want the power to be k plus r, for the first summation, k is just going to be n, because that will give us k plus r as a power. And then for the second one is also k equals n. And the third one is also k equals n. And then the last one is going to be k equals n plus 1. That will give us k plus r. So we want the power to be okay, so that's the key idea. Well, now let's see how it would look like after we have shifted these powers. So the first one, we have the sum. If k is equal to n, that means k will also start at 0. And then we have k plus r minus 1, a sub k, x to the k plus r, minus the summation of k equals 0 to infinity, k plus r, a sub k, x to the k plus r, plus the sum k equals 0 to infinity, a sub k, x to the k plus r, and the last one would change, so plus the summation. So if n is equal to 0, k is starting at 1. And then if n is equal to infinity, k will still be infinity. So then we have a sub n, well, n will be k minus 1, and x to the k plus r equals to 0. Okay. Now, let's just stare at these summations, right? So uh-huh. I lost it, right? Yeah. Yeah, I lost it on my way. Thank you. Okay, anything else? Okay, everything else looks fine. Yeah, the two got disappeared. But yeah, my mistake. Thank you. Thank you for the catch. So now that we are staring at these summations, you see how the first and the second and the third, they're all starting at 0, but the last one starts at 1. So that's what happens when you keep track of the indexing, that they're not going to all start at the same beginning, okay? So what we're going to do, we're going to write out the initial terms, meaning write out all the k equals 0 terms for the first 3 summation so that they all can start at the same k value, which is 1. So we're going to write out the k equals 0 term for the first sum and the second and the third. So then they all will start at k equals 1. Does that make sense?
Yes.
Okay. So what we're trying to do is, if whichever series is left behind, you just push them forward by writing out their initial terms. So if I like k equals 0 for the first summation, we have 2 times r minus 1, a sub 0, and then k is equal to 0, so you have x to the r. And now you can start at k equals 1, so I'm going to combine it with the last summation, so I'm holding on to that. Minus, now the second one, if k is equal to 0, we have r times a sub 0, x to the r. So now the second one can also start at k equals 1. And the third one, I'm going to write out k equals 0 term, so that's plus a sub 0, x to the r, plus, now they can all start at k equals 1, so I'm going to start writing just a single summation instead of 4, k equals 1 to infinity, and put them all together, and also factor out k plus r, x to the k plus r power, because that's the same from all of them. So we have the first summation has k plus r minus 1, a sub k, and the next one we have minus k plus r, a sub k, plus a sub k, and the last one we have a sub k minus 1, everything. So I think I forgot my 2 again. Oops. For the first summation, I forgot the 2. And then all of this gets x to the k plus r, everything equal to 0. Okay, so a lot nicer than what we had before. Now what do you notice? So I'm going to write out, so these are the k equals 0 term, right? And these are the initial terms. So check what happens with these. So if I rewrite them and factor out a0 and x to the r, so we have a0, x to the r times 2r, r minus 1, minus r plus 1, plus that giant summation, right? So that goes here. Now what do you notice? If you stare at this equation, the 2r, r squared, r minus 1, minus r plus 1, isn't that what we had earlier right here from Euler Equation? Do you see it? Right? So that's why it's okay to ignore the initial terms or ignore indexing, because indexing will just give you the terms that can be obtained another way without keeping track of the series. So that's why we're going to ignore and just work with the series without writing out keeping track of n or k. Does that make sense?
Yes, it
Okay.
does.
So we're going to ignore all of this for now. Okay, so we can ignore this because we can get this from Euler Equation. Right, so it's the same thing. So that's what we're gonna just ignore all of that. Now let's look at this summation. What will this give us? This will give us the recurrence relation. That's what we're after, the recurrence relation. So we finally have arrived what we wanted. So we have the sum. I'm gonna ignore all of this, okay? Because we have this from before. So our next step is to just write out the summation and set it equal to 0. So we have, so the coefficients of x to the kr, we set it equal to 0 and solve for the highest subscript, which would be a sub k. So a sub k, it's going to be, what is that going to be? So we have a sub k appearing 3 times. So a sub k, it's going to be someone on minus a sub k minus 1 and divided by the other coefficients. So that would be 2 k plus r times k plus r minus 1 a sub k minus k plus r. Oh, Okay, I'm making a mistake. No one caught it. So that's the coefficient of a sub k, and then the minus k plus r, and then plus 1. So that's our recurrence relation in general. Okay. But we want the recurrence relation corresponding to the larger root. What's the larger root when we solve this Euler equation? So the larger root is 1, right? You have 1 and 1/2. So the larger root will be 1. So the corresponding recurrence relation for the larger root, so for the larger root, r equals 1, the recurrence relation, so RR, it's going to be a sub k is equal to, so you plug in r equals 1, and this simplifies your recurrence relation. So that's negative a sub k minus 1 over 2 times k plus 1, k plus 1 minus 1, that cancels out, minus k plus 1 plus 1. And then you can simplify this so that when you get the coefficients, it's much simpler to work with. So I'm just going to go ahead and simplify this a little bit more. So we have negative a sub k minus 1 over, so on the bottom we have 2k squared, and then plus 2k minus k, minus 1 plus 1, they cancel out, right? So what all of this would simplify to is just negative a sub k minus 1 over 2k squared plus k. And now we can factor out the k. It looks much simpler. Negative a sub k minus 1 over k times 2k plus 1. That's our recurrence relation for the larger root. So that's the answer to the third part of this question. So any questions on this? So basically we have everything done. Any questions up to here? Okay. All right. So now let's get the coefficients, right? So how many of those do we want? We have, where is it? To compute the first 3 non-zero terms of the series solutions with a0 equal 1. Okay, got it. So we want a0 to be 1. So part 4. So we want a0 to be 1, and we want to know 4 non-zero terms. So if k is equal to 0, we get, oh, no, so k is equal to 1, because we already gave you a0 is 1. So we're going to have to start k equals 1. Do you guys see that? So do you guys see why I stopped and we start k equals 1?
Yes, because a sub 0 is equal to 1.
Right, so we're forcing a0 to be 1. That's why. So now if I do that, I'm going to find a sub 1 next. So that would be negative a sub 0 over k is 1. So that's going to be 1 times 2 times 1, that's 1, plus 1, that's 3. And a0 is 1, so let's plug that in. So we have negative 1 over 3. So that's another non-zero term. Let's go for 2 more. So if k is equal to 2, we have a sub 2. That's going to be negative a sub 1 over 2 times, so k, 2 times 2 plus 1, that's 5. So we have negative a1 over 10. Well, we know what a1 is. We just computed that previously. So that's negative 1/3. Plugging it in, we have positive 1 over 3 times 10, that's 1 over 30. So another non-zero term. Did I say 3 or 4? Let me just double check. 3. I'm done. Alright, so we're okay. We don't need any more. We have enough to write out the answer. Now let's write out that magical answer that we're after. We've been working for the last, 20 minutes. So our final solution to this, it's going to be y equals the sum starting at n equals 0 to infinity an x to the n plus r. Well, r is 1, right? That's the solution we're working with. So we're only just going to write down part of the solution. R1 is this one, and then R2 will give you another set of infinite terms. Together you'll have the general solution. So we don't really have a general solution for this. We just have a solution corresponding to the larger root only. So if r is equal to 1, we have y is equal to the infinite sum, n equals 0 to infinity an x to the n plus 1. And now let's write out some of the terms. And I'm also going to factor out x so that x to the 1 comes out. So you have, if I were to write out some of the terms, we have x times the power series a0 plus a1 x plus a2 x squared plus a3 x cubed and so on, right? We just need 3, so that's okay. So this would come out to be x times a0, that's 1, minus 1/3 x plus 1 over 30 x squared and so on. So that's the power series solution corresponding to the larger root. That's one way to express your solution. Now if you want, you could have kept the x inside the power series, so you can just distribute the x out, so you will have x minus 1/3 x squared plus 1 over 30 x cubed and so on. So 3 non-zero terms. So any of these are acceptable. Any questions on this example? Yeah.
Why do they multiply by x again? I'm sorry.
Oh, because, so what I did was I factor this out.
Oh, okay, I
Okay.
got it.
So, uh, okay, so you got it. Should I write it down?
No,
Okay. All right. So we often just factor out for the final solution, but when we're doing the work, we keep it together as an exponent because it's just difficult to work with x and then x to the n. So you just put them together. All right. So that's the beauty of this. At the end, you get a really nice solution to this. Now, if I wanted the other half of it, which was corresponding to the smaller root, that will give me another infinite series solution. And together with that one and this one, you have two independent solutions to this second order. So we only have half of the solution to this question, so we don't have the general solution. So if you want to call this y1, you can also do that as well. But I'll just call it y, it just doesn't really matter for notation in this case. So what are the steps we took? Let's just recap. Right? We did a lot of things for one problem. So we started with the question saying, show that x0 is a regular singular point. So we show that by taking limits, corresponding limits. Once we have shown that these limits, they're finite, so they correspond to specific Euler coefficients, which we call them beta and gamma. So the first limit gave us the coefficient of beta, and the second limit gave us gamma. Once we plug them in, you find the corresponding Euler equation, which is this one. Right, corresponding. And once we have the Euler equation, we have the root, because you can solve this polynomial by writing out its initial equation, which is this right here. and then we find the roots to it, we get 2 roots, 1 and 1/2. And then the next part of this question says, find the recurrence relation that corresponds to the larger root. So we compute the power series solution near the regular singular point. So the solution is y equals the infinite sum a n x to the r. We computed its first derivative, second derivative. We plug everything in, and then we start moving x variable into the summation. We modified the indexing, and then we came up with the substitution where you want all the summation x to have the power k plus r. So that's what we did next. After we did that, I show you why it's okay to ignore the indexing, because indexing will just give you the initial equation. So that's where this was, which we can just get it from Euler Equation. So why not, right? So that's what we avoid all of this, and we just take our coefficient in front of x to the r, set it equal to 0. That gives us the recurrence relation for the entire problem. But we only want the recurrence for corresponding root, which is larger, r equals 1. Once you plug in r equals 1, it simplifies to something really nice, and that's when we got this recurrence relation corresponding to r equals 1. Once we have that, we computed the coefficients, just 3 of them, and then we wrote out the solution using power series notation. And then I expanded this because I didn't want to put it in a condensed form, so I wrote out some of the terms, and then at the end I multiplied it by x. So that was the end of this question. Any questions, guys? Yep.
In section 5.2, there was a question when you ignore the indexing, one of the subscript had a negative. So it was like a subscript of -1. What do you do in that case?
Oh, they're all 0.
Okay.
So if you have negative subscript, they're all 0. So if you have negative, say a sub -1, consider them 0. So we're looking at power series solution. That means you're starting from n equals 0. So 0, 1, 2, 3, and so on. We're not going toward the negative integers. So they're all just considered to be 0. So a sub -2, and so on. They're all going to be 0. Okay, so that's something I didn't mention. Sadia, thank you.
No problem. I was doing the problem and I was like, okay, if I did the indexing, then I get the value, whatever the a subscript is like for the indexing.
Mm-hmm.
Then, you know.
Right, right. All right, good question. Thank you for that. All right, so this is it. That's 5.5, where I did one example. I'm going to do another example tomorrow, and then we'll move on to chapter 6. Chapter 6 is more fun, so I hope you guys will enjoy that too. So this is the end of our lecture today.